This is LeetCode 242 valid anagram. So given two strings s and t, return true if t is an anagram of s and false otherwise. An anagram is a word or phrase formed by rearranging the letters of a different word or phrase, typically using all of the letters exactly once. So this is silly. They don't mean typically, so I'm going to delete that. So in plain English, s and t have to have the same letters the same number of times. The example they have is anagram and nagram, and it's a little bit hard to see if they have the same letters by just looking at them now. So I'm wondering, how can we make this comparison easier? So what if we did a little bit of organization? So I'll group the A's together in S, and then I'll try to do the same thing in T. So I'll pull out the A's and group them together, and let's see what we get. Now we can examine each column in S and then try to match it against a column in T. They all match, and so they're anagrams. And in this case, we have a perfect match for every column, but what other situations could occur? We need to make sure we account for every possible situation. Well, there could be a different number of A's, like this, and that would be fine because we'd compare the 3 A's in S against the 2 A's in T, and we would see the mismatch. But we could also have a case where there are no A's in one of the words. So for example, if we removed all of the A's from T, that would still be fine, because when we examine the A column in S, we would compare it against nothing and we would notice the difference. But what if we had the case where there are no A's in S? Then, if we only iterate over these 4 columns, we'll get matches for all of them. But we won't even notice that there's this entire A column that we haven't accounted for. So how do we address this missing column issue? The obvious fix would be to just iterate over all of the columns in S and all the columns in T. And that would work because, yeah, we wouldn't notice anything is wrong when iterating over S, but when we go and iterate over T, we will notice the issue. But is there anything else we could do? I'm noticing that in this case, T has an extra column that isn't in S. So we could just count the number of columns and compare 4 versus 5, and that would work. But if I step back and think about what it really means for T to have an extra column in this specific example, it means that T has letters that S doesn't. And so we could also identify this issue by checking if S and T have the same string length. And an added benefit is that we could do this check right at the beginning before we even organize the letters into columns. But how can we represent this in code? Well, in each column, there are 2 key pieces of information, the letter and a count. So for this column, you have A and you have 3 because we have 3 A's. And in code, we could represent these pairs with a map where the key is the letter and the value is the count. Let's turn this idea into code. So right away, we can check the lengths. So if the length of S is not equal to the length of T, then we can return false right away because there's no way they can be anagrams. Now we want to create the 2 maps for S and T, and I'll use Python's built-in counter class. It will create a map where the keys are the letters and the values are the counts. So first, I'm going to import counter. So from collections, import counter, and then we can use that below. So smap will be equal to counter, and we'll pass an S. Tmap will also be equal to counter, except we'll pass in T. Now we want to compare the maps against each other. So for letter in smap, if smap letter is not equal to tmap letter, then that means we have a mismatch and we can return false. And then if we don't find any mismatches, then we can return true. Remember, we don't have to worry about the missing column issue that we talked about earlier because we have this string length check at the top. So we should be able to submit and we get a working answer. So if we comment this out and submit, we can see that it breaks. And it breaks, if you look at this example, because we're matching on all of the letters in S, but we completely miss this extra B in T. And that's because we're only iterating over the letters in S, the letters in S map. Now to fix this, of course, we could just add this back and that would work, but we could also just iterate over T map as well. And that would also work because then we won't miss this B. So let me show you real quick what that would look like. So I'm just gonna copy this and then I'll paste it here. And then we just need to change this from S map to T map. And if we submit this, then we'll be good too. So I wanted to go through that to emphasize the significance of this length check. A lot of people think that it's just a way to return early and avoid a little bit of work, but it serves a really crucial purpose. Now I'll just revert back to our original code. And the last thing I want to say is that Python does give you a lot of ways that you could condense this code further, all the way down to a single line. But I chose to be more explicit to give you a more nuanced understanding of what's really happening. Now I want to think about our time and space complexity. So we'll do time first. And I'm noticing that in lines 8 and 9, counter will have to iterate over both S and T to build these two maps. And so at this moment, I'm thinking we'll have O of S plus T. But then I want to make sure we incorporate this length check into our thinking. So I'm realizing that we'll only create the maps if S and T are the same length. And that means that O of S plus T is exactly the same as O of S plus S, and then we could simplify that to O of S. Now I want to think about our space complexity. So we have two maps, and so it seems like we would have O of S plus T. But then again, we know that if we create the maps, S and T will be the same length. And so you could simplify this to O of S plus S, which simplifies to O of S. But if you go back to the problem and look at the constraints, it actually says that S and T will only have lowercase English letters, and there are only 26 of them. So really, instead of O of S, it should be O of 26, which of course simplifies down to O of 1 space. Because we have to look at every letter in the input, we can't do better than O of S time, and O of 1 space is as good as it gets too. Before we move on to an entirely different approach, I want to talk about a popular twist on this map strategy that does allow you to use one map instead of two, but it's not as good as people think it is. It's based on the insight that two anagrams should perfectly cancel each other out. For example, if you have rat and tar, the R's cancel each other out, the A's cancel each other out, and the T's do too, and you're left with nothing. So let's turn this idea into code. So right away, we can check the lengths. And if they don't match, we know we can return false. Then we'll create one map for S, and I'll use Python's built-in counter again. So from collections, we want to import counter, and then we'll use that to create SMap. So SMap will equal counter, and we'll pass in S. Now we want to try to use the letters in T to cancel out the letters in S. So for each letter in T, we'll try to subtract it from S. And then finally, we want to check to see if everything has been canceled, and we'll know if all of the values in SMap have been zeroed out. So for each count in smap.values, if we see anything that's not 0, then we return false because that value has not been zeroed out. And if we get to the end, that means everything was zeroed out, so we can return true. It's true that this will use one map instead of two. But remember that each map can only have up to 26 key value pairs. So we're talking about 26 versus 52 at the most if you have two maps. Either way, both will simplify to O of 1 memory, all the same. But then people will say, but what if you removed the constraint of only lowercase English letters and allowed the maps to have an unlimited number of keys? Well, it still doesn't matter for big O notation. If you have one map, you could have up to S keys, which would be O of S space. And if you had two maps, you could have up to 2 S keys, which would also simplify to O of S space. So using one map is only slightly better and not in a way that matters for big O notation. All right, we've talked a lot about map approaches, but are there any other reasonable solutions? Maybe there's something simpler. Our first approach took S and T and rearranged them in the same way using a map, and then we checked to see if the rearrangements were the same. So I'm wondering, is there a different way we could do the rearranging? And if I think about this for a little bit, the idea of sorting comes to mind. If I take S and T and sort them in the same way and get the same result, then I know they must be anagrams. Okay, let's implement this sorting idea. So I'll start with our usual string length check, and now we want to sort S and T, but in Python strings are immutable, and so we'll have to copy the string into an array and sort the array instead. So I want two variables, sorted S and sorted T, and then we'll set this equal to sorted and we'll pass in S, and then same thing for T. Sorted, pass in T. And then I'll print out the types for S and sorted S so that you can see the difference and you can see exactly what I mean. So let's print type of S and then also print type of sorted S. And the output here should be string, and the output here should be list, which is Python's version of arrays. So let me run this code, and then you can see the output in standard out. So we get a string here for S, and then a list here for sorted S. Now that you know the difference between S and sorted S, all we have to do is figure out if S and T are the same after sorting. And so we can just return sorted S is equal to sorted T, and we can submit. So let's take a look at the performance compared to our previous map approaches, which took O of S time and O of 1 space. So for time, the most expensive part will be sorting, and because S and T will be the same length, it will take O of S log S time. Now let's talk about space. So heap sort can work in O of 1 space, but only if you can modify the input, which is not possible with immutable strings like we have in Python. And so if you're dealing with immutable strings, then you'll need O of S plus T space to create the new arrays, which can be simplified to O of S since S and T will be the same length. And then if you have mutable strings, which I think would be less common, then you could get O of 1 space. So for time, the map approaches are always faster, so clear win there. And there's a clear win on space too. The map approaches are guaranteed to always use O of 1 space. Now sorting could be O of 1 space, but only in certain conditions, and it could also be a lot worse. Now one nice thing about sorting is that I think it's really simple, but at the same time, so are the map approaches. And so it's worth thinking about sorting in this problem, but I don't see a good reason to actually choose it over the map approaches, which are arguably just as simple and also have better overall performance. Now, if you go back to the beginning, our line of reasoning started with examining Anagram and Nagram and asking, how can we make this comparison easier? Then we organized the letters into columns where we only saw perfect matches. So we asked, what other situations could occur, and so on, which ultimately yielded 2 map strategies and a sorting approach. What's most interesting about this problem, though, is how easy it is to get the space complexity wrong twice in 2 different directions. It's really easy to end up in opposite land, and that's exactly the trap that a lot of people fall into. If you're not careful, you can mislead yourself into thinking sorting is the space-efficient choice, when the opposite is true.